When a steel beam bends under a heavy load, it forms a continuous curve. Every microscopic point along its length reacts to the weight, creating an infinite set of data points. This continuity presents a problem for digital simulation. Computers cannot calculate structural failure across an infinite number of points. The mathematical solution is discretization, the process of breaking a continuous physical object into a finite number of manageable parts. Within this grid, each connecting line is an element, governed by a specific set of mathematical rules. For structural beams, the goal of the finite element method is to convert the physical calculus of flexure into a solvable algebraic equation. We represent this behavior using a discrete matrix system, Ku equals F. This equation isolates three components: the stiffness matrix, the displacement vector, and the loading vector. Formulating this equation for a single 1D beam element provides the core logic for nearly all structural simulation. This translation from physical bending into a discrete mathematical syntax is what allows modern engineering software to function. Building this matrix system requires looking at the mathematical origin of structural bending. The fourth-order Euler-Bernoulli differential equation serves as the governing law for how a beam deflects. This operator determines deflection and internal strain across the entire length of the beam. But finding analytical solutions becomes impossible when the geometry or loading conditions become complex. To solve this problem, we isolate one specific segment of the continuous beam to analyze it as an independent element. We begin by defining the physical boundaries of this element. We define the two endpoints of the segment as nodes. These nodes are defined by their degrees of freedom, which dictate how the element is allowed to move. Simple truss elements only account for linear displacement, but a beam element must account for the curvature of bending. First, we assign vertical deflection to each node. Second, we assign rotation. Tracking the angle of the joints is necessary to capture the internal bending strain defined by our original differential equation. By establishing these translation and rotation parameters at the nodes, we create the framework for an algebraic matrix to mimic the continuous bending behavior of the beam. With the geometry established, we can look at the external forces acting on the element. In our system equation, these forces are represented by the loading vector. This vector must account for all external loads, but it can only accept data at the specific node locations we've defined. The simplest forces to account for are concentrated loads. When a force strikes exactly at a node, we can plug its value directly into the corresponding slot in the vector. However, most real-world forces, like wind or snow, are distributed. They press continuously along the span of the beam, often missing the nodes entirely. We need a way to translate these continuous loads into discrete nodal data. We calculate equivalent nodal forces using integration. We integrate the distributed force across the element's length, weighted by shape functions. This causes the continuous pressure along the span to migrate outward, resolving into discrete vertical forces and rotational moments concentrated at the nodes. The result is a set of values that represent both the vertical shear and the rotational bending moments created by that load. These equivalent forces then populate the rows of the loading column vector. While nodal loads map directly, any load along the span must be integrated into this nodal format. The loading vector functions as a mathematical translation layer, converting continuous external pressures into a format compatible with a discrete solver. With the degrees of freedom and the loading vector defined, we can now assemble the components of the element equation. This is the expanded matrix form for a 1D beam element. The dimensions of the matrices, a 4x4 and a 4x1, map to the element's geometry, two nodes, each with 2 degrees of freedom. This equation defines the mechanical relationship between forces and displacements for a single beam segment. To simulate an entire structure, we combine these individual elements. Through global assembly, we stack these individual element matrices to form a master system for the entire structure. The overlapping regions in this global matrix represent the physical nodes that adjacent elements share. This matrix system is the core engine used by engineering software to calculate the behavior of complex structures. The internal derivation of the stiffness matrix values relies on the same integration principles we used for the loading vector. Detailed proofs for those stiffness terms can be found in supplementary technical resources. Translating the continuous calculus of bending into the discrete algebra of matrices allows us to simulate the complex behavior of entire structures through a series of linear calculations.